Alrighty, so today we're going to go over 2.2 axioms and interpretations of properties of probability. So as we write down, I'm going to write some couple of notes. So the relative frequency of an occurrence of an event can be defined as different letters. So it can be defined as A, which is the number of times an event occurs divided by the total number of times the experiment is conducted. So relative frequency, we can define it as n of event A divided by n, defined as number of times conducted, the experiment, as well as the top, number of occurrences in event A. Right? So as we go into the next one, we have also, that's 1. 2, we have the probability of an event, also defined by, let's say, A, right? Which is limited frequency of the portion A in the long run. So we can define that as probability of A equals lm n approaches infinity, right? We can ignore that, but in short is basically n A divided by n. So the same as up before. So as we scroll down, we can go over an example 2.2, which is a toss of an even coin and a number of times. We get the total number of heads that appear. So as we do, we have n, which is the amount of times the coin is flipped from. So we have 10, 100, 1,000, 10,000, 100,000. The number of times are n, which is the probability of getting a head, right, occurs. So we have 6, 54, 489, 513, and 49,100. So for example, we can do 6 out of 10, which gets us 0.6. Right, we have 54 out of 10, 100, which gives us 0.54, 0.489, 0.5013, and 0.49979. So using the formula above, we can find these calculations below. So as we move on, right, this is kind of our easy. We're going to go over our axioms of probability. So the first one, probability of A has to be greater or equal than 0. So we cannot have a probability of 0 occur. It has to be greater or equal 0, which means range from 0 to 1, which is basically 0% to 100% chance, right? Our range. Our second one is S is the sample space, which P sample space equals to 100 or 100%. We can also define A1, A2, so any event that proposes A has infinite many disjoint events. So we can define this as P A1 union A2 union ... until we get the sum of P AI, which I could be anything. All right, so other properties we can include. So the first one, right, our first other property can be A intersects B equals B intersects A. Therefore, probability of A intersection B equals probability of B intersection A. So as we do that, right, we also have some other probabilities we can also incur as well too. Some other probabilities, which is our second one, we have A union B, which B union A, which we can conclude as a therefore statement, probability of A union B equals probability of B union A. All right. So in this one, we have A equals A2 cannot equal 0, for example, and A1 union A2 cannot equal 0. All right. So our third point, we have let P probability of nothing equals 0. Right? So we can conclude that these events are destroyed. Fourth one, we have probability A plus probability A complementary equals 1. And the formula we can use for this is P A complementary equals 100% or 1 minus the probability of A, right? We can use that. Our next one, we have probability of A greater or equal to 1, right? So A has to be greater, less than. So this is less than. Then last one, 6. So we actually have more, sorry, not last one. So we have 6. If A and B are disjoint, then P, right, A intersection B equals 0. Number 7, right, for any two events, so A and B, right, we have P, A union B equals probability A plus the probability of B minus the probability of A intersection B, right? We can call this the addition rule. All right, so we can highlight this addition rule. This is very important. So next one, right, as we get to the addition rule, remember P, A, and B, right, for 3 of us, this is for 2 events. For any 3 events, right, on 8, we can have, right, so P, A, union B, union C equals probability, same thing as above, right? So we have, as you guessed, probability A plus the probability of B plus the probability of C minus probability of A intersecting B, right? Minus probability of A intersecting C minus the probability of B intersecting C, but adding now the probability of A intersecting B intersecting C. So we have adding all three probably A, B, C, subtracting the intersections of all these events, right? And using the probability of all 3 of the intersection to add it all together. Then our last one, number 9, that we can conclude, right? For the sum of probability, so sum of the probability, right? So all the probability of event A, for example, adding up. So in A, we can do a sum, right? So the sum of P A equals A1 plus A2, right? Dot, 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 dot. Okay. All right, so we're going to go over an example. I believe I wrote it over here. So we have a sample space S, which is 1, 2, 1, 3, and 5. Probability of 1 equals 0.1. probability of 3 equals 0.4, probability of 5 equals 0.8. So as this occurrence, those are the probabilities. If event A is concluded as 1 in 5, what is probability of A then? So we can conclude, right? So right here, probability A equals probability of 1 and 5 occurring, right? So as we do this, now remember P1 is 0.1 plus P5, which is 0.8, and this can be included to 0.9. Therefore, probability A equals 0.9, all right? As we move on to another example, example 2.4, which is 60% of families have TVs, 80% have internet, 50% have both, right? We have to determine the probability of a random selected family first, right? So we can denote probability capital T has TVs, right? Probability of I has internet, and then probability T and I has both, right? So we can conclude up here, we already have some of these probabilities, right? So we have P, T equals 0.6, P, I equals, right, 0.8. Now here's the tough part. We have to find P, T, intersecting I, right? So we find this, we have to kind of do a little bit of just that 0.5, so right here. So it's given in this question. Usually we'll find it, I'll explain it later. So our first part, right, we have to find if it has TV or internet. So one or the other, right? To find this, right, remember we have a union of TVs and all the places that have internet. So this equals probability of TVs occurring, adding the probabilities of internet occurring, minusing if they have both, right? This is equaling 0.6 plus 0.8 minus 0.5. We have a probability of 90% occurring, right? Our next one that we can have, right, is number 2, has none of the two cables, of the two. So we have none of them. So none of the two occur. So we have probability, people have TV, union of I complement, which is internet. So we have equals 100% minus probability of P, which we found above, union I. We include this as 1 minus 0.9 equals 0.1. So it's a 10% chance they have none of this. Third one, they only have TV, right? So if they only have TV cable. So P, T, right? We can assume this as T, if T occurs, I, internet, is not in the equation, right? So we can, that equal as probability of TVs occurring minus probability of TVs and internet occurring. So that equals 0.6 minus 0.5 equals, again, a 10% chance that they only have a TV in this probability, right? Our last one we can do, number 4, right, only has internet. So we're isolating both. So as this only has internet, right, so P internet only, which equals probability of T complementary occurring with I, intersecting I, which equals PI, which is the probability of internet occurring, minus the probability of TV and internet occurring, which equals 0.8, minus 0.5, equaling 30% chance that this is occurring. right? So using these probabilities that were given in the question and finding how the probability of each event occurring. So our next point, as we scroll down, right, we have an example. So our next example can be distributed as the following, right? As the following, we can occur this as a cloth dryer has two types. So two types, right? Electric or gas, right? We consider 5 independent customers walk in, or customers walk in, right? So we're going to find these probability as PE for electric or PG. I know it's pretty funny, right? For gas. All right, so now we have our first question. With the probability that at most one of these, purchases is electronic, right? Right, let's say it is 0.428, right? The question is now, what is the probability if at least, right, at least 2 is bought and electric, right? So we have to find these probabilities now. As we go through it, right, we're going to kind of categorize this number 1 because there's another one we have to do too. So we know, let's know what we know first, right? So we have 5 customers. We have event A, which means at least 2. 2 buy electric thing, right? P complementary A, we know, is 0, which is only buying an electric dryer, or at least buying at least one electric dryer, is 0.428, right? So as we do this, we can find probability of A occurring equals 100% minus P complementary of A, right? So we have 1 minus 0.428, which equals 0.572 is our answer. The second part of this question, right, if P equals 5 bought gas, right? So let's say that equals, we actually get a number for this one, 1.116. Then P, right, bought, right, if P bought all 5, right, brought 5 electric, right, equals 0.005. The question is, what is the probability? Is the probability at least one type is bought. Right? So as we do number 2 now, all right, we need to do P, E, and G at least bought once. Right? So we have 100% minus P, right, probability of PG, minus P probability of E. So we have 100% minus 0.116 minus 0.005 equals 0.879. So there's an 87.9% chance that it is bought. All right, so as we move on, we have one more thing, which is our equal outcomes. All right, so let's say equally outcome of an experiment. So equal outcome means, so this is defined as has an equal chance to occur. right? An example of this is tossing a coin, right? The two possible outcomes, we have outcome one is heads or tails, right? So each have a 50% chance to occur. We can define this as the formula, right? So probability A equals NA divided by NS. So this is our sample space. This, and remember, same thing as before, is a number of events or outcomes that can occur in this situation. All right, so we have another example that we can write up. So we have a fair four-sided dice is tossed twice. Right? The number of each side, we have 1, 2, 3, or 4 occurring. Right? So our sample space equals 1, 2, 3, 4. Right? But as we can kind of break this down as what can actually occur. So if we toss this, remember we're tossing this twice. So the sample space, we can have both 1s, 2, 1, 3, 1, 4, 1. Same thing, we have kind of 1, 2. Both 2s occurring. 3, 2. And then 4, 2. Then we have 2, 3. Sorry, 1, 3, I apologize. 2, 3, 3, 3, 4, 3, right? And then we have 1, 4, 2, 4, 3, 4, and 4, 4. So this is in the commas of what can occur, right? So as we do this, we have all of our sample space defined as this. So we can have event A. We can have at least, our question is at least one toss gets a 4. So this can be defined as, remember, we have NA over NS, which in this sample space we can look as, right, the number of 4s that appear only one time, which is this one, 1, 4, right? Only appears, toss a 4 only appears one time, right? We can define this as 1 over 4. And then as we define 1 over 4, right, it is a 25% chance that these occur, right? So remember, we're only looking at least one of the tosses gets a 4. All right, so you go 1, 2, 3, 4, 5, like so. Okay. So as we do this now, all right, sorry, as we go here, I'm gonna add this up here. So this was an example. I define A, we have 41, 42, 43, 44, 1, 4, 2, 4, 3, 4, right? So a sample, this is actually equals 16. So 16 events occur. 7 over 16 is our answer. All right, for B, we have the sum of two numbers that's supposed to be an N, is 5. So the sum of these can get 5. So we have 1, 4 equals 5, 2, 3 equals 5, 3 plus 2 equals 5, 4 plus 1 equals 5. This can equal probability B, 4 out of 16, and then as what we discussed before, 1 over 4. Last one is both get a 1, right? So we can only, only one of them gets 1, 1, which is this. So C, 1, 1. So the probability of this occurring is now 1 over 16. Pretty simple. All right. So as we move on, we're going through one last example. So last example, right? A drink was put into 3 cups labeled A, B, C, right? Someone's asked to taste all 3 cups in order for them for their preference. So these are 3 cups. Okay, so as we do this, we have to first write sample space. So as we write the sample space, we conclude that S, right, as occurring, what are we trying to look for on these 3 sample spaces, right? So what can occur? A person can drink A, B, C first, right? Drink A, C, B next, B, C, A, B, A, C, C, A, B, and C, B, A. And all can equally occur, right? So next question, as we write down samples, this will help us for our next couple of problems. So now we're looking for probability of A ranking first. So he drinks A first, right? So event, so this is, remember, our event equals A first, right? So as we look in the sample space, we can see A, B, C, he drinks that first, and then A, C, D, right? So this is equal to 2 out of 6, because this equals 6. And then we can get 1 over 3 as our probability of drinking, that the person drinks A first. Third one, we can say, what is the probability that A is first or B is first. So this is event A intersecting B equaling, right? So A or B is first, right? So we can define this as A, B, C, A, C, B, B, A, C, B, C, A, which also equals the probability of A intersecting B. All right, so we have 1, 2, 3, 4, so we have 4 over 6, which can be written as 2 over 3. Next one we can do, right, last one, before we end this video off, is what is the probability, so probability of A first and B last. So this event, remember, same thing, right, because we have A intersecting B, because they're both trying to get them both to occur, right? This only appears, I believe, once. Remember, we're trying to look for A first, B last. So we have A, C, B, which equals 1 out of 6 probability chance. So next one, we're going to go over the next chapter, which is combination of probability, and hope you have a great day. Take care.